हाय डियर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Hi, welcome back. This is the last theory chapter of theory part of center of mass and collision chapter, and in the next video we'll be doing the problem solving session and we'll finish up the chapter. Okay, so let's start. So here we are going to talk about inelastic collision and the relevant concept, coefficient of restitution. Okay, so inelastic collision is basically the collision where the kinetic energy system is not conserved. Okay, so some part of k, you can say some part of k gets converted into some kind of potential energy or maybe heat energy and other stuff. Okay, so this k is not conserved, so you cannot write k is equal to kf. This is not valid in case of inelastic collision. Okay, so there's one simple derivation that you can do using the equations of the elastic collision that I gave you. Like there is this k conservation. Okay, again I'm talking about the elastic collision. So this is the k conservation, and then this is the momentum conservation. Keep in mind, I can always write this momentum conservation irrespective of the fact whether the collision is elastic or inelastic, because F net is always zero. Okay, so F net is always zero. If there is no external force on the system, the internal forces are always going to cancel each other out, and F net is always zero irrespective if whether the collision is elastic or whether it's inelastic. But k is zero only in case of elastic collision and not in case of inelastic collision. So like if I'm going to use the equations of this conservation of momentum and conservation of k, we can derive one simple result, that is the velocity of separation is equal to the velocity of approach. So let me tell you what do I mean by that. So here maybe collision happens here, and then body goes like this. So this is your m1, this is your m2, and then this is your m1 and this is your m2. Before collision, this guy is moving with u1 and this guy is moving with u2, and if collision has to happen, this u1 has to be equal to more than u2. And again after collision, this guy is going with v1 and this guy is going with v2, and since this guy is going forward and impulse is acting on this guy from the back, so on this guy impulse is going to be like this, and on this guy impulse is going to be like this. Okay, so after the collision, this guy's speed must increase and this guy's speed must decrease. It happens in such a way that it's not like they are going to be colliding like one collision after other collision. So after the first collision, this is going to get v2 and this is going to get v1, where v2 will be more than v1. Okay, so if I'm going to use the equations of conservation of momentum, assuming this right hand side is my positive I, so I'm not going to write the I direction. So this is going to be m1 u1 plus m2 u2 is going to be m1 v1 plus m2 v2. This is the conservation of momentum. And for the k conservation, you can write half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Now from this relation, I can write m1 u1 minus v1 is m2 v2 minus u2, and from this equation I can write half m1 u1 square minus v1 square is equal to half m2 v2 square minus u2 square. Okay, and now suppose this is one equation and this is equation number 2. I'm going to divide equation 2 by equation 1. So this again half cancels out, this m1 cancels out, m2 cancels out, and then I can open this up. This is going to be like u1 minus v1 into u1 plus v1. So all I'm left with, if I'm going to divide 2 by 1, gives me u1 plus v1 is equal to v2 plus u2, and that basically says u1 minus u2 is equal to v2 minus v1. Okay, So this is the velocity of approach. Okay, so this particle m1 is approaching particle 2 with a relative velocity of u1 minus u2, and then again this after the collision v2 is going away from particle, or m2 is going away from particle m1 with the speed of v2 minus v1. Okay, so this is the velocity of approach and this is the velocity of separation, and that is same in case of elastic collision. Okay, so there's this term defined as coefficient of restitution, and it's E, and it's defined as velocity of separation divided by velocity of approach. Okay, now think about it. Now this velocity of separation, velocity of approach is same in case of elastic collision. Okay, so for elastic collision this is going to be same, so E is going to be equal to 1. Okay, now suppose the particle sticks. If this particle collides on this particle and it sticks to it, so if they are going to stick together, obviously they are not going away, so velocity of separation goes to 0. So for sticking case, this E goes to 0. Now you also have to keep in mind that, like, if the particle is sticking, obviously it cannot be elastic collision. Okay, so this is a case where the coefficient of restitution is 0, and this is also known as perfectly inelastic collision. Okay, where E is going to be 0, or anything that is not 0, that is not 1 is going to fall in case of like inelastic collision. So for elastic collision E is going to be 1, and for inelastic E is going to be equal to 0 and less than 1. So more than 0 and less than 1. So it can be anything less than 1 and more than 0 and equal to 0. Okay, so this concludes the topic of inelastic collision and the concept of coefficient of restitution, and we'll see, like we'll learn about these topics in greater detail in the next section. Okay, so let's move forward. Okay, so here is a simple scenario, and I have a particle here of mass m, and there's a smooth surface. Okay, so there's no friction. Okay, and this particle is like coming or moving with a velocity v in this direction. Okay, so this is the arrow, this is the direction of the velocity, and it the velocity vector is making an angle theta. So if this line is making an angle theta with the normal. Okay, so if I'm talking about the vector, and this as the normal direction, this as the normal direction, this is going to be minus of normal direction. Okay, so with the minus of normal direction is going to make an angle of theta. So just think about this angle theta, and again this angle is also theta. Okay, and we have to discuss the motion of the particle after the collision. Okay, so after the collision it might be moving with some speed u, and it might be making some angle phi here. Now we have to discuss what the value of phi and what the value of u is going to be if the collision is different, like in different cases. So suppose the collision is elastic, in that case find the value of phi and u, and if the collision is inelastic, in that case find the value of u and phi. Okay, so if the collision is elastic, one thing we can be very sure of is that there is no loss of kinetic energy. Okay, so this half m into v square, it has to be equal to half m into u square. So without any calculation, we can say that this speed with which it's coming onto the surface is the same as the speed with it's going to leave the surface. Okay, so the speed is going to be same because the kinetic energy has to be same. So this v is going to be equal to u. Now think about it. This smooth surface cannot exert any kind of force parallel to the surface. Okay, because there is no friction. If there were friction is going to act parallel to the surface, and in that case the momentum of the particle in this direction, suppose this is I and this normal is j, so in this I direction is going to change if there is a friction. But since there is no friction, no momentum in this direction is going to change. The only change momentum is going to be from the from the j component. Okay, so this surface is only going to exert force in the normal direction, not along the tangential direction. Okay, so this momentum of this particle in the I direction initial. So this is I, or since I is also initial, I'm going to call it x. So momentum of the particle in the x direction initial case is going to be same as the momentum of the particle in the x direction in the final case. Okay, so here suppose initial momentum, so the particle velocity vector is something like this. So this vertical component is going to be cos theta, this horizontal component is going to be sin theta. So the initial momentum is mv sin theta, and suppose this moving with speed v, so u, so in that case I can write the momentum in the x direction is, this is m into u, this will be mu cos phi, and this will be mu sin phi. So this is going to be mu sin phi. And since we already know, since the this collision is elastic in nature, so v is equal to u, so this v is equal to u, so this mu and this mv cancel out, and I'm left with sin theta is equal to sin phi. That means phi is also equal to theta. Okay, so as you can see, if the collision is elastic, the particle speed as the incoming speed is equal to the outgoing speed, and it's going to make the same angle theta. So you can also think in that term, like the angle of incidence is equal to the angle of reflection. Okay, so that is the case for elastic collision. Okay, so can we say the same thing about inelastic collision? Let's try it out. So if the collision was inelastic, and again I'll just quickly draw the figure, and this is my theta and this is my phi. So this will be u, this will be some v, and finally suppose it's u. Okay, so in this case obviously I cannot use the conservation of energy equation. Okay, I cannot use the conservation of energy equation. So this obviously this u will be less than v, because there is a loss of kinetic energy. So final speed is less than the initial speed. And again there's one simple relation that again I can write if the surface is smooth, and that is the pxi is equal to pxf, because again the surface is not going to exert any kind of force in the horizontal direction. So I can write pxi is equal to pxf. So I should be able to write mv sin theta is equal to mu sin phi. Again m cancel out, so here I'm getting sin v sin theta is equal to u sin phi. And since u is less than v, so like u by v is less than 1, that I can write. So u by v is equal to sin theta by sin phi, and this whole thing is less than 1, that means sin theta by sin phi is less than 1, that means sin theta is less than sin phi. Okay, so in this case you should be able to see, like if sin phi is more than sin theta, then obviously phi must be more than theta. So in this case again I can write this thing, that phi is more than theta. Okay, so if the collision is inelastic, this angle of reflection is more than the angle of incidence, you can say in this case. So this is the angle of incidence theta, and this is the angle of reflection, so this phi is going to be more than theta. Okay, so but how do we solve it? How do we know what is the speed u? So in this case one additional information will be given, and that is the coefficient of restitution. Okay, so if you want to calculate the value of u, obviously you'll need the value of phi, or if you need the value of phi, you will need the value of v. So here generally one more information is given, like the coefficient of restitution, and that is basically the velocity of separation divided by velocity of approach. So in this case I'll just make a demarcation here. In this case the value of e will be given, and that e is the velocity of separation divided by velocity of approach. Now keep in mind the separation velocity is always along the line of common normal. Okay, and approach is also the same velocity along the line of common normal. So this is the separation along the common normal, and this is the approach along the common normal. Okay, and also keep in mind this is the relative speed. Okay, so here the surface is not moving, so the approach speed with which this particle is approaching this plane is v cos theta. v cos theta. Okay, so again in this case also it's v, and this vertical component is going to be v cos theta. So that is the speed with which it's going to approach. Again, the horizontal speed is not going to be included in the approach speed, because I can have a surface like this and there is a particle moving with a velocity u parallel to the surface. Okay, so this height is not changing. Okay, so it's moving parallel to the surface, it's never approaching the surface. So what is the velocity of approach? In this case it's 0. Okay, so if the particle is moving parallel to the surface and it's not approaching, the distance between the particle and the surface is not changing, in that case approach velocity is going to be 0. Okay, so this particle is approaching, the approach velocity is always the velocity along the perpendicular. Okay, so the common normal, and that is v cos theta. So here you will be given this information. Suppose E is given, so you can write E is equal to V separation, and again it's going with U, so separation is U cos phi and approach is V cos theta. Okay, so here this relation will be given, and then again using this equation and using the momentum equation, you can derive or you can figure it out any value, maybe theta or maybe u. Okay, so this concludes our collision chapter, and in the next video we'll do problem solving. Okay, so stay tuned. Okay, thank you.